In this brief video, we will illustrate the motion of a harmonic oscillator using a Mathematica program. This is something that we will do a number of times this semester and next, so I thought we'd start here with something very simple, which is the harmonic oscillator. So here's the canonical model with the mass in a spring with its linear restoring force, or equivalently quadratic potential. That gives rise to this equation of motion, x double dot equals minus omega squared x, where omega is the square root of k over m, as you well know. Now, one thing that we haven't shown, which is kind of interesting, is that we can actually take this second order differential equation and write it as a system of two first order differential equations. So we can write it x dot is 1 over m times the momentum. That's well known. Just a definition of momentum. And then we can say that p dot equals minus kx, right? Because p dot is the force. And these two are equivalent, but here now I have two first order differential equations instead of one second order. And that can be convenient in some cases, as we'll see. It has these solutions. This is the position, this is the velocity. We've seen this a number of different times. And this is the Mathematica program. Set the time back to 0 there. Here's the potential with c not 0. And here are the turning points. We're starting out with the mass at the turning point and 0 velocity. And we can change the energy a little bit like this. Then we can turn on the time, and we can see how the mass is moving as a function of time according to the known solutions over there. Okay, I can stop here somewhere. We can adjust this to this point, for instance. So here we have at this particular time, the position is 0, but the velocity is at its maximum, because now we are above the equilibrium point, so we have a lot of kinetic energy, and therefore the velocity is maximal. So you already all know that. Now, this is not the main point of this. What I really wanted to do is introduce a couple of other different ways of displaying the solution. So here again we have the potential. This is now the position and the velocity in purple, just like on the previous plot. We have a couple of other plots here. This here is the momentum versus the position. This is known as a phase plot, where we're plotting, both p and x. Both of these two variables are plotted at the same time. And this is convenient because the state of a harmonic oscillator depends not only on position, but also on its velocity or momentum. So any point in this phase plot uniquely determines the state of the harmonic oscillator. That's not true on the x-axis. So for instance, if you look at this point here, the position is 0, the velocity is negative v maximum. All right, and then I can step time forward, and now we're back to x equals 0, but now the velocity is positive. So those two positions or configurations are different, even though they correspond to the same position of the harmonic oscillator. If you look, however, on the phase plot here, as time evolves, the position moves around in this ellipse here in the px plane. And the interesting part is that, let's move this back to 0 again, that this position here with negative velocity, that's here in the phase plot. And with positive velocity, it's up here in the phase plot. So those are two distinct positions, and that makes life simpler. So the phase plot is something useful that we will use extensively next semester when we work with nonlinear dynamics. We can also illustrate here the original position, the starting position here. It's x naught, p naught. If you move that around, that's possible to do here. And that, of course, also changes the position after some amount of time. So we can start out, if we like, with a motion that's at the equilibrium point, but with some net velocity. And then we get a different position, different time evolution, which starts from maximum velocity and 0 position. Over here, we've just plotted a times this exponential minus I times omega t minus phi, or deltas that we used over here. This is just a convenient way to plot the motion of the harmonic oscillator, and really why we are using the exponentials in this case. Okay, so like I said, this gives you perhaps a little bit of insight into the properties of the harmonic oscillator. We will use this extensively later, and I will make this available. Oh, one other thing I wanted to mention. As you can see, when we let time evolve here, the position in the phase plot keeps changing, and if I change the energy, then we're moving in a different orbit. There is one specific point that is different, though. If we have the energy 0 here, then the position is at the center here of the phase plot, at the origin. This is what's known as a fixed point. If you put your system at this configuration, it will stay there. That's the characteristic of a fixed point, and it's very useful in analyzing differential equations in general. And for harmonic oscillator, it's very simple. The fixed point is just at the origin here of the x and p plane.